Welcome back to the wonderful world of astronomy. This is chapter 3 on the science of astronomy. And in this video, we'll look at astronomy in the Renaissance. Where my video left off last time in part 2, we had the Ptolemaic model of the universe. So there was Aristotle's model that had the sun or the earth at the center of the universe. Claudius Ptolemy in the 2nd century AD added to that the planets, as they move around the Earth, travel on little circles. And for many, many centuries, since the 2nd century AD, that was the standard model of the universe, that all the planets move on small circles, moving on larger circles, orbiting around the Earth. And as the centuries went on, astronomers were able to more accurately, more precisely measure the positions and the movements of the planets in our sky, and the Ptolemaic model wasn't accurately predicting as well where the planets should be. And so over the many centuries as they went by, the Ptolemaic model got much more complicated as they kept adding to it and adding to it. What they really needed to do was throw out the old model and start fresh, but they didn't think to do that. They just kept with this model of the Earth at the center and kept adding more and more features to it to try to make it look like the motion of what the planets were actually doing in the sky. And that really didn't change until the Renaissance. And so we'll look at the Copernican revolution during the Renaissance. So here we have the Renaissance and the Copernican revolution. And this time frame is about the 15th to the 17th centuries. And if you study Renaissance history, you see that in a variety of ways, there was an opening of thought throughout Europe. There was a time of great social change during these centuries as we moved out of the Dark Ages and into the Renaissance. It was the beginning of exploration, the beginning, it seems, after many, many centuries of man wanting to explore and learn more about the world around him. For example, it was the beginning of scientific inquiry, the beginning of what we know of as modern science, the idea that you can do observation and experimentation, and that would help us learn about the world. It was the beginning of, as I mentioned before, exploration. So many of our great explorers in history going out into the world and discovering new places, that was during the Renaissance. It was the beginning, I shouldn't say the beginning, but it was the opening up of religious thought. And this is the time of the Protestant Reformation when the printing press was invented, the Bible was being produced so that people could read it on their own and not just take their word for it that the church leaders told them was in the Bible. They could actually read it, and they said, what you've been telling us for centuries is in the Bible isn't actually in the Bible. So it was the opening up of religious thought. It was the opening up of artistic expression. So many of the great artists in world history came about during the Renaissance. Well, we're going to look at the astronomical advances during the Renaissance and see how it shaped modern astronomy. So astronomers of the 16th and 17th century. In this video, we're going to look at 3 men who made great contributions to astronomy and shaped it the way into becoming the way it is now. We're going to look at Nicholas Copernicus, who considered the sun to be at the center of the universe instead of the Earth. We're going to look at Johann Kepler, who mathematically described the orbits of planets around the sun. And finally, we'll look at Galileo Galilei, who was the first to observe the heavenly bodies with a telescope. Let's start with Nicholas Copernicus, lived from 1473 to 1543. He proposed a sun-centered model of the universe that was published in 1543, actually the day that he passed away. Nicholas Copernicus used the model to determine the layout of the solar system. Now, in the previous video, I showed you that Aristarchus an ancient Greek man, he had considered and written about a sun-centered model of the universe. So Nicholas Copernicus found his writings and was intrigued by them. Now, the problem with Nicholas Copernicus's model with the with the sun-centered, so the heliocentric model, was that his model was no more accurate than the Ptolemaic model in predicting planetary positions because it still used perfect circles. And remember the ancient Greek notion that heavenly bodies move in circular motions, and that was just this assumption that they relied on. And as long as he was still sticking with circles instead of elliptical orbits that we now know them to be, his model was going to be a little bit off in predicting the motions of the planets. Nicholas Copernicus was not an astronomer. He was actually a minister in the church, very well educated. Astronomy was more a hobby of his, but he wanted to explore nature, and he, agreeing with the psalmist in Psalm 19, who said, "The heavens declare the glory of God, the skies proclaim the work of his hands." He wanted to see this glory of God that was being proclaimed by the stars, by the heavens. And so it was a pursuit of his that led him to become one of the most famous astronomers in the world. He wrote a book titled On the Revolutions of the Heavenly Spheres, and in it he wrote, "All the spheres revolve about the sun as their midpoint, and therefore the sun is the center of the universe." Now, this was so heretical to what most people believed at the time. It was firmly believed, and it had been firmly believed for millennia, that the Earth is at the center of the universe. Nicholas Copernicus knew that he would get much trouble for expressing such a view, and he was not interested in getting trouble, but he was interested in publishing this. And so he asked his family not to have it published until after he died. And in fact, it was either the day of his death or the day after his death that his family published it. And so this very controversial notion that the sun is at the center did not go over well. And in fact, somebody, not Nicholas Copernicus, but added in a later edition an introduction explaining that the heliocentric model that Nicholas Copernicus proposed, that the book was proposing, was merely a tool for calculation. So it was basically wimping out. And so somebody added in later that we don't actually believe this to be true. This is just something, it's a hypothetical thing to help with calculations. And the quote says, "These hypotheses need not be true or even probable. They are put forward merely to provide a reliable basis for computation." Well, Nicholas Copernicus certainly didn't believe that. His book shows that he honestly believed that the Earth was that the sun was at the center of the solar system, in fact, of the universe, and that the planets moved around it. So Nicholas Copernicus's book was not held in any high regard, and most scientists just went on believing in the old Ptolemaic model of the universe. So again, this was published in 1543. Now, as the decades went on, some scientists started to come around to thinking maybe Nicholas Copernicus was right, and that leads us to our next guy, Johann Kepler, who lived from 1571 to 1630. So keep in mind the timeline here. He was born a few decades after Nicholas Copernicus passed away. Kepler first tried to match the observations that he made with circular orbits. So he very painstakingly observed the motions of the planets in the sky, hour after hour, night after night throughout the years, and he was trying to come up with a mathematical model of where that could predict where the planets are. And the circular orbits were not working for him. There was an 8 arc-minute discrepancy in the motions of the planets that led him eventually to think about elliptical orbits. So think about what 8 arc-minutes is. Remember, a circle divided up into 360 degrees. So a degree is a thin, very thin angle. Then you divide a degree up into 60 arc-minutes. So 8 arc-minutes was this tiny little angular distance discrepancy between where his mathematical model of circular orbits, planets moving around the sun, where that showed, and where the planets actually were in the sky. And there was this little discrepancy that was bothering him. And he wrote, if I had believed that we could ignore these 8 minutes of arc, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore, those 8 minutes pointed the road to a complete reformation in astronomy. So Johann Kepler considered what would happen to the mathematical model if we assume that planets travel as they go around the sun, not in circles, but as ellipses. So quick geometry lesson here. Let's think about a circle and what exactly defines a circle. If you take a pin and a string and you attach the pencil to the string and you move it around where it'll go, it will trace out a circle, and the pencil is the radius of the circle away from the pin. Now let's have a more complex structure. If we pin down a string, just like you see there, a focus here and a focus there, so the two foci, those are where the two pins are, and make a triangle of the string with the pencil, and you move the pencil around, constrained by the string, it will make an ellipse. Now, an ellipse, you can think of it as an oval, as an elongated circle. And we talk about how stretched out, how elongated it is as its eccentricity. So over to the right here, an ellipse with an eccentricity of 0 is actually a perfect circle. But as we move the foci away from each other, then we have a more eccentric circle. And ellipse. It is elongated from being a circle. And as we move them farther apart from each other, we have a highly eccentric ellipse. Now, when we talk about the size of the circle, we can talk about the radius from the center to the circle itself. When we talk about the distance across an ellipse, what matters is what direction you go. On this picture, if you go from top to bottom, that's a shorter distance than from left to right. So from top to bottom, we call that the short distance, we call it the minor axis. From left to right, that's the greater distance across, we call that the major axis. What's important to you for astronomy vocabulary is not the major axis, but half of the major axis, the semi-major axis. So from the middle across the major axis to the end, that's the semi-major axis. The reason that's important is when we talk about the motions of planets around the sun, we'll talk about the planet's average distance. Sometimes the planet will be a greater distance, sometimes a smaller distance from the sun, but the average distance we call the semi-major axis. Johann Kepler came up with 3 laws of planetary motion. Now remember, what is very astounding about this is these 3 laws that we still recognize as being true. They apply actually to all things, not just planets, but all things that are in orbit around a central gravitating body. So it also applies to comets going around the sun. It applies to moons going around a planet. The astounding thing is that he came up with this in the early 1600s. And he did this all from just observing the lights in the sky, the motions of the planets in the sky. Kepler's first law says the orbit of each planet around the sun is an ellipse, with the sun at one focus. So here we have our ellipse, the motion of the planet around the sun. The sun's at one focus, and there is nothing at the other focus. There doesn't have to be, but the sun is at one focus. Here is the major axis. And remember, the semi-major axis is the average distance from the sun. Kepler's second law says as a planet moves around its orbit, it sweeps out equal areas in equal times. Remember these two vocabulary words, perihelion and aphelion. So when a planet is closest to the sun, right here, that's called perihelion. When it's farthest away, it's aphelion. So equal areas in equal times. In the same amount of time, let's just in this picture arbitrarily call this a month. It'll sweep out, so you see this blue area right here, it sweeps out an imaginary line from the planet to the sun, sweeps out some area. Well, when it's farther away in the same amount of time, it's going to go a shorter distance because it needs to sweep out the same area. Shorter distance in the same amount of time, let's call it 1 month, means it goes slower. So near perihelion, in any particular amount of time, a planet sweeps out an area that is short but wide. Near aphelion, in the same amount of time, a planet sweeps out an area that is long but narrow. So what this means is that a planet travels faster when it's nearer to the sun and slower when it's farther from the sun. And I want you again to think about how astounding it is in the early 17th century that somebody came up with this, and it was true. It is a correct representation mathematically of how planets move around the sun, this idea of sweeping out equal areas in equal times. So here we have a visual animation of this. You can see as it gets closer to the sun, it goes faster, and as it gets farther, it goes slower. Kepler's third law of planetary motion. The more distant planets orbit the sun at slower average speeds, obeying the relationship p squared equals a cubed, where p is the orbital period in years and a is the average distance from the sun in astronomical units. Okay, so the farther away planets are on average, the slower they will go. That sounds a lot like the second law, but I want you to remember the difference between the second law and the third law. When you're thinking about the second law, the equal areas and equal times, that is referring to just one particular planet. It's talking about a single planet as it moves around. When it's closer to the sun, it's faster. When it's farther, it's slower. Think of the third law as a comparison between two different planets in their entire orbit around the sun. If a planet is farther out from the sun, such as Neptune, very far from the sun, it will go slower. It'll take more time to go around. And a planet that is closer to the sun, like Mercury, it will go faster. It takes a shorter amount of time to go around. So Mercury takes about 88 days to go around the sun. Of course, Earth takes 1 year. You go farther out, Jupiter takes about 12 years to go around, and it goes like that. So p squared equals a cubed. Orbital period is related to the average distance from the sun. This graph, based on Kepler's third law and modern values of planetary distances, shows that more distant planets orbit the sun more slowly. So here we have on the horizontal axis average distance from the sun in astronomical units. You know right here at 1, Earth is 1 astronomical unit away. Jupiter is a little more than 5. Saturn is about 10. And you see the average orbital speed. Now Kepler's third law, that equation doesn't deal with the speed. So this is showing something else, but this is actually showing how fast they go. So Mercury is the fastest, then Venus, then Earth, Mars, Jupiter, Saturn being the slowest of those. Now, Kepler did not have a theoretical basis for this. So if you had asked Kepler, why do the planets obey these laws? I don't know what he would have answered. Probably something like, I don't know. He did not have any theory, any reason behind this. He was just showing mathematically what he was observing in the sky. This was in about the 16 teens. He published between 1610 and 1618, and it wasn't until Isaac Newton came along towards the end of the 17th century that we finally had a theoretical model, an explanation for why the planets do this. So a thought question. An asteroid orbits the sun at an average distance of, so there we have an average distance, A equals 4 astronomical units. How long does it take to orbit the sun? This question is applying Kepler's laws of motion to an asteroid, but remember, as I said before, it applies to anything in orbit to anything else. So 4 astronomical units. Let's think about this. The Earth is 1 astronomical unit away, and it takes 1 year to go around. So certainly the answer is going to be greater than 1 year because it's farther away than the Earth. Well, all these multiple choices give an answer more than 1 year. How long does it take to orbit the sun? We have the equation that period squared equals semi-major axis cubed. And so we take the semi-major axis, which is 4. Let's cube it. 4 cubed, which is 4 times 4 times 4 is 64. So here we have p squared now is 4 cubed, which is 64. So the period, whatever it is, squared is 64. Well, conveniently, the square root of 64 is 8. And so what number squared is 64? Well, that's 8. So an asteroid that goes around at an average distance of 4 astronomical units has a period of 8 years. And this allows astronomers even today, if they know one variable, they can solve for another. So if we see maybe a comet, an asteroid, going around the sun, and we see it again a few years later, we can calculate, based on its period, how far it goes from the sun. Or if we know how far it is on average from the sun, we can calculate its period. We can calculate its trajectory. The third astronomer who made great advances in astronomy during the Renaissance is Galileo Galilei. He was a contemporary of Johann Kepler. Remember, Kepler published his work about 1610 to 1618. Galileo, his contribution is by using the telescope, he overcame major objections to the Copernican view. So certainly Kepler believed in Copernicus's model because he came up with mathematical description that relied on the sun being at the center. Galileo showed observational proof that anybody, I shouldn't say proof, he showed observational evidence that anybody could look at and see for themselves things that helped us to get rid of the old Greek notions of astronomy and accept Copernicus's model of the universe. He made the first astronomical observations with a telescope. He's often credited at inventing the telescope. He did not. The telescope was invented by somebody else in about 1608, but it was within a year that Galileo got a telescope, about 1609, and made the first observations of things in space. So I want to look at what did he observe that was so profound. First thing, he observed craters, mountains, and valleys on the moon. What did this have to do with the Copernican revolution? Well, for millennia, going back to the old Greek notions, there was Greek philosophy that said that the things up in the heavens were perfect jewels, the jewels of the gods, and therefore they were circular, they were spherical, they were perfect and unmarred. And Galileo showed that there were craters, that there are blemishes on the moon. And it did a little just to detract from the Greek notion that everything up there is perfect. And so he showed these imperfections on the moon. And he did the same with the sun, showing sunspots. The sun was no longer regarded as this heavenly jewel up in space, but rather it has blemishes on it. And if these heavenly jewels, what they used to think of, the sun and the moon, weren't so perfect after all, then maybe they're not spherical, maybe they're not going around in circles around the earth. Maybe other things we thought, such as the earth being the center of the universe, other things that we thought like that aren't true as well. He observed Jupiter's four largest moons, and these moons are named after him. Collectively, they are known as the Galilean moons, and they are named Io, Callisto, Ganymede, and Europa. And this is a typical picture. If you look with a simple telescope, this is what you might see if you look at Jupiter, those four moons as they go around Jupiter. And this is a very astounding discovery because he could see day after day these moons moving around Jupiter, in orbit around Jupiter. It's an astounding discovery because he discovered something out there that has things in orbit around it. And if there's something out there that has things in orbit around it, then that took away the specialness of the Earth. Then maybe Earth itself is in orbit around something, such as the sun. Here is Galileo's notes. So night after night, we can see this looks like I think calendar dates: the 2nd, the 28th, the 30th, the 2nd, the 3rd, the 3rd, the 4th, the 6th. So calendar dates looking at the Jupiter and the different moons and their positions. So day after day, he drew a picture of what he saw in the telescope of their different positions, and eventually he was able to conclude that they were moving around Jupiter. So he showed that not all objects in space orbit the Earth. He also saw phases of Venus. Venus goes through all different phases: the crescent phase, the gibbous phase, all the different phases, just like the moon. And the Ptolemaic model of the universe cannot explain all the phases of Venus. So let's think about the Ptolemaic model that has Earth at the center, and there's the sun going around the Earth, again in Ptolemy's model, and Venus closer to the sun. So Venus orbits the Earth, moving around a smaller circle on its larger circle. So remember the epicycles. If this view were correct, Venus's phases would range only from new to crescent. So right here would be new, it would be crescent, it would be new again, and crescent, and we would never get gibbous phases. However, in reality, here we have the sun at the center and Venus, and then Earth going around a little farther away. In reality, Venus orbits the sun, so from Earth we can see it in many different phases. This is just what Galileo observed, allowing him to prove that Venus orbits the sun. So here we have new Venus, crescent Venus, quarter, gibbous, full, gibbous, quarter, crescent. And you notice also when it's a crescent, it's closer to us than when it's gibbous. And so here we see pictures of Venus, modern photographs of Venus, and with size comparison. And it is bigger when it's a crescent because it's on our side of the sun. When it's a gibbous, it's on the far side. So in size comparison, it's going to look smaller. Galileo was punished for publishing and talking about his belief that the Earth was not the center of the universe, that in fact the sun was the center, at least of the solar system. The Catholic Church ordered Galileo to recant his claim that Earth orbits the sun in 1633. His book on the subject was removed from the Church's index of banned books. Finally, in 1824, they came around and realized a few centuries later that Galileo was correct, and Galileo was formally vindicated by the Church in 1992. So in this video, what have we learned? How did Copernicus and Kepler challenge the Earth-centered idea? Copernicus created a sun-centered model. Kepler found a model that fits observations, meaning a mathematical model. What are Kepler's 3 laws of planetary motion? 1, the orbit of each planet is an ellipse with the sun at one focus. 2, as a planet moves around its orbit, it sweeps out equal areas in equal times. And number 3, more distant planets orbit the sun at slower average speeds, and they follow the equation that the period squared equals the semi-major axis cubed. What was Galileo's role in solidifying the Copernican revolution? His experiments and observations overcame the remaining objections to the sun-centered solar system model. And that's the end of part 3, Astronomy in the Renaissance. Have a great day.